작년에 이어서 두 번째 PNU 리서치 콘서트입니다. 우리가 축제 가수도 부르고 좋은 시간을 많이 보내는데 we have now also many foreign guests here. It's wonderful here. It is exactly what we should do in future. 내 영어를 이해해 주시겠죠? Even though we have many festivals, even with inviting very famous pop singers and so on, but why not? We invite our wonderful researcher, even from PNU. It is very important. Therefore, I initiated last year such a PNU research concert. Research is not only for in the lab or in the university. It should be propagated to whole human beings and this generation. Especially, he is working also this climate changing, which we very well know. Yes, we have today PNU Research Concert with inviting Professor Axel Timmermann. Actually, I didn't know before he introduced himself. We graduated same German university. It was what a coincidence. Therefore, he becomes one of my best friends here also. Also, he plays piano, and I plays also violin. Therefore, we play all together quite often, as much as possible. Yes. Now, I introduce Professor Axel Timmermann, and please enjoy his wonderful talks, and also very welcome any question or any discussions. Thank you. Please continue.
Thank you very much, Ingwon, for the nice introduction. I have to apologize for the fonts. They all got screwed up because my Apple computer did not work. So we have to work with Windows today. So please apologize for some of the aesthetic glitches. Okay, I would like to start with a question here. What do burning trash dumps in India, whale dating, and an octopus in a Miami parking lot have in common? So they all seem very unrelated. Anybody an idea what could be the unifying subject for all of them? Nobody? All right, well, CO2 is the answer. Why? What does CO2 have to do with whale dating or burning trash dumps in India? Well, the whale dating is the following. Ocean acidification, and we will talk about it more in detail, it's an effect of CO2 being taken up by the ocean, decreases the absorption of sound in the ocean, which means whales can communicate much better over long distances. They can find their mates by their whale songs much more easily in future. The downside is, of course, the ocean will get much more noisy, so there will be more noise pollution as a result of ocean acidification. But for whales meeting each other, that's a very good thing. Now, what about the octopus in the Miami parking lot? Well, it turns out sea level has already risen by about 30 centimeters over the last century. You can see it every year now. Sea level rises by about 4 millimeters per day. It's visible. It's not per day, per year. So sea level rise is of course happening, and Miami is very close to the shoreline, very close to sea level, and it's in a very porous old limestone area, so seawater can easily come up in the city if we have high waters. And as seawater comes up, also all sorts of marine creatures come up. So this octopus in the Miami parking lot found 2021 was a result. It came up because sea level has already risen by 30 centimeters, driven by CO2-induced global warming. Now, what about these heat what about the trash dumps in India? Well, global warming, of course, intensifies extreme heat waves. Not every heat wave, of course, but in general, we see a trend in the heat waves becoming more intense and more frequent. And so these trash dumps, they release methane. And because there were such high temperatures in these trash piles, there was a spontaneous combustion which created massive fires which were very difficult to extinguish. So we see these are seemingly unrelated things, and you can think about your everyday life. What may have changed in the last 50 or 100 years? What was climate like? What were the environmental conditions like of your grandparents or grandparents? And you can already see that climate change is not a thing of the future, it's something that's happening right now, and we are already in the midst of it. Okay, so as you heard, I'm the director of the IBS Center for Climate Physics, and there are some eminent physicists sitting here, and the question is, of course, what is climate physics? Why do we talk about climate physics and not climate research? Well, let me just say, physics is essentially a way of understanding nature quantitatively with equations that we can derive from first principles. And what we do in climate physics is we use the equations of physics, and we'll come back to that, to understand and predict past, present, and future climate change and Earth system changes. And I wanted to give you just an idea here. The normal climate system, of course, has many different phenomena. You may have heard about ice ages. The El Niño Southern Oscillation phenomenon has been in the media recently because one strong El Niño might be developing currently. We are just almost entering in about 2 or 3 weeks the Jangma season. So these are all natural phenomena that have been around on our planet for a very long time. They have nothing to do with global warming. And we would also, in our center, like to understand these phenomena and monitor them as well. So we are very much interested also to understand how past climate changed. But now, of course, there is a new part in the equation, and that's humans, and in particular fossil fuel burning. So we emit CO2 and other greenhouse gases, and that creates additional global warming as well as other things that we'll discuss later on. Well, I don't know why these fonts have been flipped, but that's Windows, I guess. So they are sabotaging Apple. Global warming is, of course, a result of this. And we can ask the question, well, how does global warming actually also influence some of these natural climate phenomena? Is the Jangma going to become stronger in future? Are we going to see more or less El Niño events in future? And another result is, of course, ocean acidification that I mentioned in the context of the whale dating, but whale dating sounds like fun, but I think there are some very severe consequences of ocean acidification that we will also discuss. Okay, the main carbon problems. I hope that works, okay. The main culprit is, of course, fossil fuel burning. Our daily activities contribute to this, and that of previous 3 generations. And they come with influences, impacts on several systems. We talked about global warming is a result of heat trapping, wrong wave radiation trapping due to the greenhouse gases in the atmosphere. It can enhance extreme events. It has already intensified heat waves, and it will do that also in future. And it also contributes to sea level rise because of 2 factors. One is water expands when I warm it up. So that's number 1 factor right now. And also global warming creates melting of ice sheets and glaciers. And that also adds extra volume to the ocean, leading to sea level rise. And that has impacts on livelihoods worldwide already. Ocean acidification, we will look at this in more detail, can cause a loss of biodiversity, maybe even food insecurity on our planet, because a lot of our planetary population is still growing. So we need more proteins actually from the ocean, and that might be at jeopardy unless we cut down CO2 emissions. Ocean hypercapnia is something that we don't really understand very well yet, but it's an interesting research question. So essentially, if we are in this room here for the next 10 hours, which we won't, so don't worry, the CO2 level will go up in the room and we will all get very tired and so on. So CO2 at very high concentrations becomes toxic for animals, including ourselves. And so at CO2 levels of 1,000 parts per million, many organisms, fish in particular in the ocean, can feel this hypercapnia, the toxicity of CO2, and they will change their behavior. They will get, I don't know, dizzy, or they will be much less responsive in the presence of predators and so on. Okay, and also as a result of fossil fuel burning, we have a lot of air pollution. So that's, I think, currently the main killer, and as you know, air pollution is responsible for millions of premature deaths worldwide. Okay, so you can imagine many different impacts on societies and ecosystems: displacement, climate-induced migration, shortage of drinking water, ecosystem collapses in the ocean and on land, changes in the virus preferences or parasites, if we think about malaria. So certain mosquitoes that are the carriers of the malaria parasite, they like it warm and moist. So the warm and moist areas, they will expand as a result of global warming, so we may see many more areas that will have the increased health risk. Okay, so we would like to understand what can we do about it. And well, we may think we just shut down CO2 emissions. That's going to be easy. Well, let's see. Sure, that's the right pathway, but we also have to keep in mind that the CO2 that we are pumping into the atmosphere will stay there for a very long time. CO2 is a very inert gas that we can take up by plants, photosynthesis. The ocean takes up a little bit, but most of the CO2 that we are burning today, let's say 2000, in about 10,000 years, still 30% will stay in the atmosphere. So the CO2 that we are emitting today, if you like, a large fraction of it will still be there for many, many, many generations down the road. So this is called the carbon legacy problem. So there are two aspects to that. One is that we have to act immediately to cut down CO2 emissions, to lower the CO2 concentration curve. The other one is also that maybe in future, in order to scrap down more CO2 from the atmosphere, we also may need new technologies. But right now, these technologies are not readily available. Okay, so let's think about the carbon legacy. And there is one important statement, maybe a take-home message for you. That is, we have already changed our climate system irreversibly. Why do I say that? Well, the CO2 emissions we can cut down by 2050. But the CO2 concentrations, they will level off at a high level. So it's the concentration is the aggregated emissions, if you like. And so all the fossil fuel burning that has happened over the last 100 years, much of the CO2 will still remain in the atmosphere for a very long time. So cutting down the emissions is the right thing to stabilize the CO2, but we are stabilizing the CO2 at a higher level. As a result of this, well, hopefully we can be able to stabilize temperatures, even though there is a delay effect in the system, and you can have a situation where CO2 stabilizes, but temperatures still rise for many more centuries. But there is currently no technology available which will allow us to bring our temperatures back to the level of pre-industrial, 1850, for instance. We can cut down the CO2 emissions, but it's not going to bring back our temperature to the level of 1850. This is why I'm saying climate has already changed irreversibly. Okay, so then there is a big issue because the ice sheets, they are integrating these warming factors much more gradually and slowly. And it turns out that if you warm our planet by more than 1.8 degrees, and we'll come back to that, our ice sheets, the Greenland ice sheet and the Antarctic ice sheet, will start to melt irreversibly, which means they will contribute to sea level rise for a very long time. So all we need to figure out right now is how quickly should we push down the CO2 emissions in order to even slow down this curve. Because this is going to be our, not this carbon legacy, but this is also the climate and sea level legacy that we're creating. Okay, let's talk a bit more about bending the curves. I mean, the emission curves. Well, these are the global carbon emissions in gigatons CO2 equivalent per year. And you see we have about 36 right now. And well, who knows what the scenario is, what our politicians decide or how we will react. But this is something we call a scenario in climate research. This would be a possible pathway. In this case, once we are at zero emissions, also the CO2 concentration will start to stabilize, and so will our temperatures. As a result of such a scenario, we would end up with a temperature rise relative to pre-industrial conditions of about 3 to 5 degrees Celsius, depending on some of the climate models that we're using. Okay, so very easy. Well, if we do carbon neutrality by 2050, and Korea has, of course, pledged that this is going to happen, as well as many other countries. We can talk about the action later if we are on the right path, but this is at least, the words are going in the right direction. CO2 concentration will level off at a much lower level, and we will end up with a smaller warming, maybe of about 2 degrees Celsius. Okay, so are we on the right path? What's actually happening? And it's good to take a look at what we call carbon bombs. It's a dramatic word, but actually it's a good word. A carbon bomb is a project that is able to burn or to pump at least 1 billion tons of CO2 into the atmosphere. And these are all the known carbon bombs that we have. So it means we know there are, 43 billion tons of carbon, oil and gas in Qatar, for instance. The decision is now, okay, are we going to use the existing resources? Are these countries still, and the oil companies still making money from this? Or will they say, no, we just don't want to make profit, we will keep our climate system stable? That's kind of the decision. And if we put all of these carbon bombs together, we end up with about 650 billion tons that are kind of already in the planning of being emitted. Okay, this would push us way beyond 1.5 degrees Celsius, which was the more aggressive target of the Paris Agreement. So Antonio Guterres, he said to this carbon bomb thing, investing in new fossil fuel infrastructure is moral and economic madness. And I can't agree more with him. Okay, so let's go back to the science. So there will be a few sprinkles of non-science in there, but I think it's a societal problem. So how can science help? Knowledge, prediction, solution? Well, let's see. Just a little introduction here. So this subject of climate change has received attention. Of course, the Intergovernmental Panel on Climate Change received, together with Al Gore, they received a Nobel Prize in peace. The first climate Nobel Prize went to peace, not to physics. The second one went to economics. That's William Nordhaus, because he put a dollar amount on carbon. He started to talk about carbon economics. And then only 2022, 2 years ago, the physics community recognized the physics of climate change as a major contribution to mankind's knowledge. And these guys, they are economists. They didn't really talk much about climate change. They invented mechanism design and reverse game theory. This is now used for cap and trade and carbon trading systems. It's a way of punishing and incentivizing behavior. So it's a mixture of psychology and economics. Works very well. So these guys are actually developing ways to modify policies by governance that can be implemented to cut down CO2 emissions on a global scale. They're not fully aware of their contributions, but they definitely developed a nice scientific framework to do that. Okay, how can basic science help avert climate damages? We'll talk first about climate research here. And let me just... Oh, that was one too much. Okay, oops. Here we go. Okay, climate research. What do we actually do? We, as I mentioned, are climate physicists. We use the equations of the climate system in order to understand how it works and how it responds to external forces. So and our main tools are climate models. What is a climate model? Well, a climate model is just a collection of equations, physics equations. So we have to deal with thermodynamics, okay, heat, we understand that, fluid dynamics, because the atmosphere and the ocean can be treated as a fluid dynamical system. We need to deal with quantum mechanics in a very simple way, because the absorption of long-wave radiation by CO2 that causes the greenhouse effect is a quantum mechanical feature. And we need to deal with electromagnetism, which means light and infrared radiation properties in the atmosphere. So this is, in a nutshell, a climate model. All of these equations are complicated, and we have certain processes that we cannot fully resolve. We can't resolve every tree on our planet. We can't resolve every cloud that's being generated. So we have what we call parametrizations. So these are still equations, but they use more empirical data. They're not as much based on first principles as the upper ones. And that's where the uncertainty sometimes in climate model projections comes from. Okay, and then we need something that no physicist can predict. This is politics. So what kind of CO2 scenario are we going to use? Are we going to shut down emissions or not, right? We can't say that. So neither, well, that's something that we have to run as a scenario. So we run different pathways. Let's say we have a very stupid pathway where we just emit business as usual, or we have a smart pathway where we make sure our future generations have a safe climate. This is what we do. And now these equations are so complicated that we cannot solve them by hand, no way. So we need computers, and does a laptop work? No, it's not enough. So a typical computer model is a code, a programming code that has about 1 million lines of code. And so it's typically 20 years or 30 years of work that flows into the building such a computer model. It's a very complicated thing. And we use Fortran as a language. Many of you may not even know what it is, but it's an old language which is very powerful still on these supercomputers. And so in the middle you can see our computer that we purchased in 2019 for our center. It's the Aleph supercomputer, but it's not here in Pusan, even though I tried. It didn't work out. It's now in Daejeon at the IBS headquarters. And just keep in mind, a climate model just solves equations. It's not a statistical model. We don't do any statistical extrapolations or so. Okay, a few words on computer modeling. The first real climate model, and I showed this gentleman, Suki Manabe, who got the Nobel Prize 2 years ago. He worked in the late 1960s on the very first atmospheric models, and they were run in Princeton on a machine which was able to do 1 million calculations per second. Then I joined the Max Planck Institute in 1995. They, at that time, purchased a Cray computer, which was able to do about 10 to the 10 floating point calculations, so already factor 10,000 faster. This is approximately the speed of your iPhone nowadays. So then, in 2004, I joined the International Pacific Research Center in Hawaii, and we had access to the Earth simulator in Jamstack. The huge computer was as big as a soccer field, just one computer rack after another one. It needed so much power that it had its own power station, actually. That was another so 4 orders of magnitude. And then we bought Aleph in 2019, and that had about 10 to the 15 calculations per second. So we call this is essentially 1.5 times 10 to the 15 calculations per second. And then now our German colleagues, they got a new computer which is able to use even faster speed to access, to crunch the numbers of our climate system. And in the early days, the climate models included only the atmosphere. Later, they included also the ocean together, and eventually the biosphere, so land and also stuff in the ocean, living things in the ocean. And only very, very recently, also in our center, we have started to include the ice sheets as a fully dynamic component of our Earth system. So Greenland and Antarctica. Okay, I said already a few things about this. We can just show you some animations here. So you run a climate model and what comes out is zeros and ones, right? So that's like what a computer does. So now we need to put these zeros and ones back together to make sense of them. And this is going to show you the temperatures simulated by a climate model that we are running. You see California here, and you can see all of these little, we call them eddies and turbulent structures. All of this is actually simulated. It's not, there is no observations that goes into your climate model. This is all coming out as a result of the equations of physics. And I still always think this is actually amazing how well physics works. So this is just one illustration here of ocean temperatures. Let's look at the water vapor in the atmosphere. So this is, we're going to see precipitable water in the atmosphere. And this is maybe winter time. We will see essentially a seasonal cycle here. And yeah, you can see now the northern hemisphere gets a little bit more water vapor. You can see some of the tropical cyclones, typhoons developing. Again, no observational data used here. Now this is, if we increase the atmospheric CO2 concentration, the whole thing just gets much redder, which means we have much more water vapor in the atmosphere. And we'll come back to that because that's a driver for extreme events. We just have the warmer atmosphere can hold more moisture. Okay, then I think, yeah, let's go to this one. We use the same climate model. At the time when we ran it, it was, I think it was the highest resolution climate model simulation conducted so far. So Sun Son Lee, who is sitting here, she conducted these experiments on the Aleph computer. And so we can run the climate system, now a very high resolution globally, but for different, as I mentioned, scenarios. So this would be business as usual. We don't cut down CO2 emissions, we just continue. And in that case, by 2100, Korea would warm up by 4 degrees Celsius, the Arctic by 10 degrees, okay? Now, if we continue even beyond that to 2150 approximately, we would see almost doubling, so 8 degrees warming above present day, not pre-industrial present day, and the Arctic would warm up by more than 15 degrees Celsius. So that's a lot. So you can imagine these would be major changes. Okay, what does it mean, for instance, for Korea? I wanted to illustrate that with heat waves. So what we're seeing here is the number of days per year of daily maximum temperature. And the blue one is for current conditions. So you can see, well, in Daejeon, well, there are just very, very few days on average where the maximum temperature increases over 40 degrees Celsius. However, in future, 40 degrees Celsius, we will have many, many more days every year. And if you look at it, so the current worst extreme events, those guys, they become the future summer norm. They become a typical summer day, unless we cut down CO2 emissions. So this gives you some idea how bad things can turn out on a regional scale. And this is a weather forecast here for present day conditions. Heat wave in Seoul and Daegu, 35 degrees Celsius, and may happen this year quite easily. So what's going to happen in future? Well, these forecasts can change to much more dramatic temperatures unless we cut down CO2 concentrations, CO2 emissions and concentrations, hopefully too. Extreme heat waves in South Korea will impact livelihoods, agriculture, energy consumption, outdoor labor, a lot of things in our societies. Okay, that's the temperature story. What about the rainfall story? And I'm moving now to the other side of the Earth, Europe. And as you know, Mediterranean is quite dry. That's why we have good wines there and good olives and so on. But with global warming and the same simulation, continued business as usual, the rainfall over Europe will drop dramatically by about 25% if we don't take any further action, continue business as usual, 40% rainfall reduction. That's like the Mediterranean becoming close to desert. So this is something very dramatic. It will affect agriculture. It will affect water availability for millions and billions of people. So this is a potential effect, but this is just an illustration to show what's happening if we don't cut down CO2 emissions. Okay, now there is, I mentioned already, you saw this animation of water vapor in the atmosphere. So as we increase the CO2, there will be more water vapor. Warm air holds more moisture. And this means if it rains in future, there is more water that can come down as rain. And that intensifies that strengthens or increases the intensity of rainfall events. So we can look at this in this map, was generated also from a computer model simulation that we ran on the Aleph computer. And we are looking here at the number of occurrences of extreme precipitation events of more than 100, is essentially, which occur typically only once in 10 years. So a 1 in 10 year event. Under present day conditions, the entire map would be 1. Okay, so what we are seeing is how frequent, or what's the amplification and the frequency of these events. And we can see Korea will experience 3 times more of these extreme rainfall events that nowadays occur only once every 10 years. In future, they will occur 3 times every 10 years. However, over the Himalaya region, there is a factor of 15. So an event that happens only once every 10 years will become like an annually recurring event. And that's pretty dramatic because also keep in mind this is the area where many of the major rivers of Asia start, so they will also contribute to a lot of the flooding in future if these major rainfall events occur over a larger scale. Okay, so another thing that of course in Korea we are worried about, it's not typhoon season yet, but typhoon season will come shortly. Typically August, September. And so we can use these climate models to look at how the frequency of and intensity of these typhoons changes. Okay, again, I'm just showing you an illustration. This is from our computer model. Again, the beauty of physics. These flying donuts that you're seeing there are tropical cyclones generated by Aleph. They have nothing to do with the reality, but we can look at how the statistics of these tropical cyclones, typhoons, changes as we increase the CO2 in the model. Okay, I mean, these are some dramatic events that hopefully will not happen this year, but this is something, of course, a typical year under present day conditions. Okay, let's see what's coming out of our calculations. All right, so this is work done by a former researcher in our center, Jong-in Chu. So she looked at the simulated tropical cyclones, and you can see all of their tracks under normal conditions, and then we can see the change in density of these tracks if we increase the atmospheric CO2 concentration. And what we see is that mostly there is a reduction in the tropical cyclone density, which means there are fewer ones. There are some areas where there are more. So what we find is that overall, the tropical cyclone numbers globally will decrease. And we can say, well, hooray, that's a relief. There is going to be less damage in future. However, it turns out, even though the global number decreases, so this is for CO2 doubling, quadrupling, which hopefully never happens, But the strong ones, so category 3 and up, they become more intense. So we will have more strong ones and less of the reduction in the number of weaker ones. However, if there is a tropical cyclone, as I mentioned again, we have more moisture in a warmer atmosphere, and that's going to be dumped as extreme rainfall. So if we look at the rainfall associated with landfalling tropical cyclones, typhoons, it will increase depending on the atmospheric CO2 concentration dramatically. So we can see there will be a factor of 10% to 25% increase in the rainfall associated on average with a tropical cyclone globally landfalling. Okay, so bringing this back home, there are these interesting headlines. I hope it's not going to happen, but anyways, it was in Yonhap News. South Korea seeks to build new Busan airport as country's first floating airport. I'm not sure if this is still in the books, but you wonder, okay, if in future we don't cut down CO2 emissions and we have this intensification of very strong ones, is there a way of building or making a floating airport typhoon safe? I don't know, maybe this is already considered, but these are questions that should be answered because the lifetime of an airport is typically 50 to 100 years. So if we do long-term planning, we need to take into account the information from the climate models. We can't just say, okay, we'll just extrapolate. No. Okay, now, sea level rise, I mentioned, this is work also done by a PhD student in our center. So he looked at what happens with the Antarctic and Greenland ice sheet if we warm our planet. And so this is only the sea level contribution from the ice sheets. So if we cut down CO2 emissions very drastically, okay, 2100, we can manage to bend the curve. You remember we talked about this hyperbolic curve, but we can still bend it. And this is when we cut down CO2 emissions to a level where we keep our temperature at 1.8 degrees above pre-industrial conditions. Now, if we go above, you can see that the shape of the curve, or the curvature, actually changes from something like this to something that becomes exponential or hyperbolic. And that's pretty bad. That means it's a runaway and irreversible anyways. So if we don't cut down CO2 emissions, 2150, only the ice sheets themselves will contribute 1.4 meters. On top of this, you will have the expansion from the warming of ocean water, which adds another 1 meter. So by 2150, you can end up with easily 2.5 meters. That's in 120 years. So many of the students' grandchildren, they will probably experience that. And which means we have to invest in infrastructure, but also for some regions, Bangladesh, for instance, where 100 million people live essentially close to sea level, we have to expect climate or sea level induced migrations. How are we going to deal with this in the future? Okay, I will skip this food security issue, or maybe not. You can see the typical productivity of a crop. This is wheat, for instance. If it's too cold, it doesn't generate much. If it's too warm, it doesn't work, because also we don't like it too warm. Put ourselves too long in a spa and we will not be happy. Same with plants. So you have a rapid drop in the yield of a crop. Now, this is right now where most crops worldwide, they're planted to use this optimum yield. Now, with global warming, of course, the temperature will move to the side here, which means many crops will experience this drop in the yield or in the productivity. And so there are estimates that crop yields of rice, soy, wheat, etc. May decrease by about 8 to 10% per degree global warming. And keep in mind, this is happening at a time when the global population may still increase. Okay, so until 2100, some estimates suggest 30 to 40% crop reduction in countries India, South Africa, and the Middle East. So food insecurity is going to become another major driver for political and geopolitical tensions, I suppose, and loss of lives. Okay, let's talk about the ocean acidification. Well, we burn CO2. Sorry, we burn carbon. CO2 gets into the atmosphere. 28% ends up in the ocean. And there it creates a nice looking reaction. We create first carbonic acid. That further dissociates into bicarbonate and a proton. The bicarbonate further dissociates into carbonate and another proton, and there is a balance there. Now, what's the big business here? Well, why is it actually bad? Well, keep in mind, we have a lot of organisms in our oceans, such as seashells, corals, everything that forms calcium carbonate, and there are different types of that. They use the following reaction: calcium plus carbonate, which normally is in the ocean abundant, relatively abundant, and it forms calcium carbonate, strengthens their survival and everything. Okay, now we blast CO2 into the atmosphere, reacts with ocean water, steals the carbonate, and you generate two bicarbonates, which are boring. But the stealing of the carbonate means we will have a reduction in the formation of calcium carbonate. It's not that simple, but this is something which needs to be further investigated. This is really an important nexus between human effects, chemistry in this case. This is not global warming. We only talk about the chemical effect of CO2 and biology. Okay, who might be most affected? There are different types of calcite. This one, the high magnesium calcite, is the most vulnerable one. Aragonite is also quite vulnerable, and keep in mind, coral reefs will already be affected a lot by temperature rise. So there's a famous coral bleaching effect, and there are other creatures that are less vulnerable in the future. So again, you can imagine there will be winners and losers, and we don't know how this is going to affect the global ecosystem. And that's something to further investigate. But there is a chance that many of the calcifying organisms will be affected in a negative way. Okay, how does that work for Korea? Well, this is again a computer model simulation done in our center. Korea, right now you see this dashed line, and under present day conditions, the dashed line is kind of North Japan, and this is the line where typically these calcium carbonate forming organisms will feel stress. It doesn't mean they can't do anything, but they will be affected by stress. And unless we cut down CO2 emissions, the following will happen. This line will move southward, equatorward, and Korea will be actually in an area where this calcite formation will be reduced dramatically. So we don't really know who is going to be most affected by how strong, but this is really interesting research also for students to get involved in. It's a very fundamental problem. Here's an illustration: a happy pteropod, a little sea snail at present day conditions, 380 parts per million CO2, and this is a similar one for elevated CO2. And you can see this guy can't barely move, and also the entire shell is extremely brittle, not providing any support or as a shield. Okay, coming back to the whale mating, there is this other interesting effect that the protons that we are generating in the reaction that I showed early on, they react here with borate in order to create a different substance which has a lower sound absorption capability. So this is one of the main sound absorbing materials in the ocean. So by decreasing the pH in our ocean, meaning we make it more acidic, we can reduce the sound absorption by about 50% in future. This is illustrated here. So again, good for whales if they want to find somebody. They just shout out and they can reach longer distances, but bad because the ocean sound pollution will increase dramatically, and that can have a lot of negative influence on the marine mammals. These are just some examples. Okay, how can basic science avert climate damages? Well, we talked about the main the main culprits, the main factors. So what about, can we give some advice on adaptation? Well, and again, there are these two sides, how to deal with the carbon problem. Adaptation is one, where we can say, okay, this is going to happen to Korea, and maybe then the Korean governments will say, okay, we need to upgrade our infrastructure, we need to build not a floating airport, but another airport, who knows what. So there could be many examples. Flood protection, disaster management, could be done on a regional scale or a global scale. Mitigation is much more an effort that only works if all the countries do it together. To cut down CO2 emissions, not only one country can pull the weight, so everybody has to pull the weight together, but the regional implementations can be different. Energy efficiency, clean energy, sustainable transportation, these are just a few keywords here, and I can mention a few more, but we want to know for adaptation, what should we actually adapt to? Right? Okay, it's going to get warmer, right? So that's something that is probably quite clear, but specifically, can we have quantitative assessments what to do? And yes, again, this is where these supercomputer climate models come in. For Busan or Seoul, we can calculate for different scenarios what's going to happen. Let's take a look at temperature. Okay, if we don't cut down CO2 emissions dramatically, well, our planet will warm, and so will Busan, and so will Seoul and Pyongyang and whoever. Okay, what about rainfall? Rainfall is interesting. The change in mean rainfall is not very dramatic. But what you see is actually that the change in the extreme rainfall is much more dramatic. So that's something that we discussed earlier on, the factor 3 for extreme rainfall, 3 to 5 actually, depending on where you are. So this is relevant because now you can translate this into water management or planning of new reservoirs, for instance. You can translate this into power generation, because if this is going to happen, we probably need to have a different grid as well, and so on. So there are a lot of factors that will come out of these climatic changes: flooding, disease outbreaks, typhoons, fires, outdoor labor. So there are many different sectors in our society that will be affected if we don't cut down CO2 emissions. So, but we have quantitative information in these climate models that can be used for better decision making. Okay, and this is a great challenge in Korea to bring these communities, the stakeholders, and also climate scientists together on the same table. Good. This is, I already showed this, the daily maximum temperature, illustrating the most extreme heat wave that you experienced in the last 10 years will become almost like the summer norm if we don't cut down CO2 emissions. This was the factor 3 to 5 of intensification in the extreme rainfall going from present day to future. So we need to upgrade our water infrastructure dramatically. You can ask the question, the basement apartments in Seoul, is that if this is going to be the trend in future, going from low probability to high probability, what about the basement apartments in Seoul, depicted in this movie Parasite, and of course last year's flooding in August. So there are things that actually, if you know they will intensify, that can trigger action, hopefully. Okay, when you can also use it, you can use these forecasts and say, well, if this is all going to happen, if we can't do much about it, well, maybe there is some positive stuff that we can get out of it. Well, if we don't cut down CO2 emissions, you can say, well, let's take a look at a climate model, and what we see is actually there will be more sunshine over Korea. 1 hour per day on average, that's a lot, which means we are intensifying the photovoltaic potential capability quite substantially. So it would be good at least to invest in solar rather than in other technologies. So there is information there. How this is going to get translated into society, to stakeholders, to action is another question. Okay, how can basic science help avert climate damages? Mitigation, I will skip this out of interest in time. What time is it anyways? 20. Okay, so I still have 10 minutes. All right. Good. So maybe I should show the last slide. This is actually a nice web page. You can go to this one, and you can try to solve the carbon problem yourself. So this is a simple climate model coupled to an economic model and a carbon cycle model. And it's online, so there are these sliders. You can play with these sliders, and you can try to cut down. So the standard is we don't do anything. That's the normal slider position. And in order to cut down from 3.6 degree warming in this model to 1.6 degree, you can move these sliders. And it's actually quite difficult. It's very difficult to get down to lower than 2 degrees Celsius. There is not a single silver bullet. You need a portfolio of solutions. That's what it tells you. You need to without carbon price, nothing will happen, actually, because there is no incentive for the fossil fuel industry to do something different. Transport, so yeah, transport contributes a little bit. Buildings is all good on a global scale. Deforestation, methane is actually very powerful, and this discussion has been around for a while now, that it might be meaningful to cut down much more on methane emissions in the very beginning in order to get us on the right track. And reforestation also contributes. So actually the message here is, even if you think technology is going to be great, we're going to make better energy efficiency in buildings, we will drive all electric cars, globally, that's not going to be the solution. It's a contribution to the solution. So politicians worldwide and also in South Korea, they need to work on all of these sliders and implement the effect of these sliders. Otherwise, we are not going down the right pathway. It's kind of a nice illustration. Now, are we on the right track? Well, there are, of course, lots of promises. In 2022, despite all the promises, countries trying to get carbon neutral by 2050, or some countries later and others a bit earlier. So still, despite of that, 4 countries are considering to build new coal plants, not gas, not PV, coal plants. Okay, China will stop all overseas coal plants, okay, but not in their own country. India will reopen 100 power plants. This is all present. This is all 2022. In 2022, 1 year ago, but methane levels had the largest annual increase ever. Not the annual value, but the increase even was strongest. Deforestation in the Amazonas area is up 70% compared to 2021. Are we on the right track? I sometimes really wonder. And then also the countries pledged they will put a lot of money into supporting climate action and supporting developing countries in taking the right measures. There is a compensation issue right now also. Climate action support will miss the 2023 goal by $100 billion US. So we are so far away from the right track that I really wonder what's going to happen with our generation, well, next generation and next generations. So bending the emission curve, what can we do? All the fonts got screwed up a little bit. Anyways, that's difficult to read. Okay, so let's talk about these ones. Oops. That all got, anyways. Economics. Carbon dividends is an incentive. So incentives are important. Well, you also want punishments, right? So somebody who uses a lot of carbon, even though there is better energy available, they should get punished because that's going to affect future generations. So carbon taxes, and these two should go together. You can think about international situations, policies, governance, and of course national policies and international treaties, they have to work hand in hand. Then on a more, let's say, personal scale, what can you do? We'll talk about it a bit more. Local products is important. You don't have to export your radish for your kimchi, or so. There is enough radish probably in Korea, or if not, then you can plant more. Education, saving energy. So this is actually really important. Our personal contribution, our personal responsibility. In Korea, the discussion right now is all about technology. Oh, we're going to do this, we're going to build this, and so on. But actually, that's not going to be sufficient. Without our personal action, and also means sacrifice, we are not going to be on the right track. Saving energy, this is the energy issue here, saving energy, renewables. There is discussion right now about carbon capture and utilization storage units, drawing down CO2 from the atmosphere. The technology is not scalable right now. Maybe it will be scalable in 50 years, but still the Korean, the governmental carbon neutrality committee has made a big point saying, okay, CCUS will be important even by 2030, even though we have no safety regulations or anything for that. So there are certain ways that to go forward here. And I wanted to say a few more words on the energy part. I will skip that one. The incentive part is quite easy. You give you punish those that use a lot of CO2. Somebody who wants to buy a new fossil fuel combustion car, well, maybe they should pay extra, right? Just give them ask them for 5 million more in taxes. That money goes into essentially supporting cars, give them a tax deduction that have less CO2 or actually drive electric. There's still maybe CO2 in the background, but they are still more efficient. Maybe in the first year it won't do much. And of course you need the infrastructure. So 1 million per car could go into building infrastructure, charging stations and so on. Okay, do that 1 year, maybe nothing changes. Do it 2 years, 3 years. These things will change. Economics is a very strong driver for change, social change. And so this is a way where eventually the general public will benefit. So carbon tax incentive or dividend system is feasible, has been suggested in many economic contexts, statewide and also globally, statewide and nationwide. Same thing you can do here. Think about fueling up your car. You can pay an extra tax that goes into carbon fund. If you don't drive a lot, you will get actually a dividend out of the fund at the end of the year. Kind of nice, so it's like neutral. If you don't use any CO2, you will get back quite a nice check at the end, or maybe a tax dividend. Part of it can also go into investment into renewables. So there is a way by which you can change the course of behavior. And the best way is to do it, or most efficient and fastest way is to do it, well, combination of education, but also economic carbon tax dividend systems. Okay, so Korea has a problem. Has anybody seen that movie Don't Look Up? Yeah. Okay, anybody else? Not many people. It's a nice movie. It's really worth watching. And it's a bit of a, they don't talk about global warming in there. It's a comet gonna hit the Earth and everybody's just denying it and don't look up because there's a comet there. And then I think Korea has a problem. I call it the don't look up problem. Why is it don't look up problem? What do we see up there? There is no comet hitting our Earth. That's good news. There is other good news there. Actually, there is a lot of sunshine in Korea. It's very easy. I come from Germany, and this is the photovoltaic power production potential over Germany, and you see everything is blue anyways. Germany with bad weather, cloudy days, with higher latitude, still 8% of solar energy, 8 to 10% of the electricity comes from solar energy. Korea is way behind, even though this is really nice location, lower latitude, so more sunshine, great weather, and so on and so forth, relative to Germany. Okay, so we are far behind here in South Korea in implementing solar energy and photovoltaics. Then there is another interesting point if you think about, again, economics. Just from an economic point of view, what should we do? And this is for global. It does not apply for every country the same way. But if we just look at the price, levelized cost of energy per megawatt hour, okay, what we see is, well, the solar panels, PV, they were really expensive a long time ago. Well, not a long time ago, actually 13 years ago. And we all knew, okay, that is not going to work. But the price has dropped down so much, so we are right now at $40 per megawatt hour, and that's nothing, as compared to nuclear energy, which is 4 times as much. So these are the levelized energy costs. Levelized means this is for a new plant that can generate this amount, and for the new plant, you need to include the the production cost, the operation cost, the incentives, as well as the decommissioning costs. Put everything together, and also the supply of resources. And in the meanwhile, it turns already out, and this is true globally, that wind and solar are the cheapest one. And given the fact that Korea is actually a really good latitude and has a good climate, this would be, I think, a very safe way forward. Of course, there are issues with storage, right? So these are volatile resources. You need to come up with ways of storing the energy, but this is also not rocket science. Okay, personally, and I'm running out of time, there are lots of things that you can do, and you probably all know them, and you're probably already all doing them. And it goes from eat local, drink filtered tap water, don't buy plastic bottles like these ones. Bitcoin mining is really bad because it uses a lot of computer time, so just get rid of your Bitcoins. They're too volatile anyways. Dry your clothes outside. Well, it's not easy in an apartment, but you don't need to dryer necessarily, and so on and so. Also, PNU, this is actually quite nice today, but we were in a seminar room the other day where the temperature, I don't know, was freezing cold, was 15 Celsius or something like this. It's not necessary. It's not necessary to overcool or overheat. We have, our human body is much more adaptable than that. So there are many ways how personally you can get involved, and this is all your own personal choice. But anyways, there are options. Global warming, well, there is a way of getting carbon neutral, and for me, I think the world will become that, hopefully, uses smarter decisions, smarter technologies, and the right decisions based on the available resources, natural resources that we have. In Korea, that would be sun and wind. Okay, these are just a few things that I didn't mention. Put a price on carbon to account for damages is important. Introduce carbon tax dividend system, divest from fossil fuels, regulate Bitcoin mining. Cryptocurrency is still a big thing in Korea. Tax incentives for photovoltaic, improve efficiency, very important actually. We are very inefficient in using energies, and also buildings are not very well insulated. Deregulate wind farming implementation. One of the main problems why we don't have more wind farms in Korea is there is so much red tape regarding the regulations. Invest in green hydrogen technology, introduce carbon auditors. The government should have carbon auditors. We have financial auditors, and we can have carbon auditors. Invest in science-based adaptation strategies, and so on and so forth. So get rid of carbon bombs. These are just many, many things, and I could go on for another hour on this one, but time is out, and I think I will just leave it here. Carbon neutrality, well, is not a walk in the park, but it's more, it requires teamwork, some sacrifice, and most important, dedication and action. Okay, thank you for your attention.